In our previous lecture, we obtained the impulse response for an RC circuit, and how we obtained the solution was we guessed the form of the solution, and we put that guess into the differential equation, and differential equation gave us the unknown in our guess. So we obtained the impulse response through that guess. But today we will try to reach the same conclusion from a slightly different path. Okay. Namely, we will now obtain the impulse response by another approach, namely the limit approach. Okay. So this was the circuit that we studied in the previous lecture. Okay. This is the source. We have an LTI resistor and our capacitor, CR plus minus VC. And this is our output of interest, the capacitor voltage. Okay. So by definition, impulse response is from the input, you apply unit impulse function. Initial conditions of all dynamic components are 0 by definition. Okay, and then you go and check the response at the output, and what you see is called the impulse response of that circuit. Now, in this simple circuit, what we have is we're applying, this is our input, therefore, from this input we're applying the unit impulse function, and we're going to figure out what the capacitor voltage is as a result. Now, since this function, impulse function, is a little bit hard because it's non-standard, hard to deal with due to its unbounded nature. So let's therefore, in this lecture, try to deal with it through its bounded version. Okay, and then we make that bounded version more and more close to the impulse function, and then we see what happens to the response in the limit. So what we mean is the following. So we approximate the unit impulse t by the pulse function. Okay. So pulse function has this shape. You're familiar with t, let's call it p delta t. So it's 0 for all negative times, and for a while it's constant. Okay, at some height, let's call it, 1 over delta, and then after a while it's again 0, and the delta is such that, or the area is such that no matter what delta you choose, it's always 1. Therefore, the width and the height must always give the product of 1. Okay, so this is the pulse function. Okay, and as delta goes to as delta becomes smaller and smaller. Okay, so as you squeeze the width further and further, 1 over delta has to increase, so the height becomes larger and larger, and in the limit we say this becomes the impulse function, delta function. So we can express this pulse function through sum of 2 steps. Okay, step functions, ut minus ut minus delta over delta. It's a step, and that's a delayed step. You take the difference, and then what you do is you scale the height with 1 over delta, and this is at the end of this expression you obtain this pulse function. Okay, so let h delta t denote the response due to the pulse function P delta t. P delta t. Remember that without this delta h of t was the notation that we used to indicate the impulse response. Okay. Then we have the following. Suppose that this is an LTI circuit and all the initial conditions are 0. Okay. And then this arrow indicates the input, and here we have the output. So this notation that means that for an LTI circuit with a single input and some output of interest, what you apply is, from the input is the pulse, P delta of t, and then what you get at the output, we're calling the pulse response, and we define the pulse response with h sub delta of t. Okay. And as for the same circuit, and again, 0 initial conditions. If you apply from the input unit impulse function, what you get at the output is what we're calling the impulse response, okay, h of t. Now, here is a simple observation that we make. Since this pulse becomes closer and closer to delta t, okay, as this delta, capital delta, becomes smaller and smaller, so that would imply, therefore, as you squeeze delta further and further, this response becomes closer and closer to impulse response. Okay. Once again, as delta goes smaller, as delta goes to 0, okay, as delta becomes smaller and smaller, I'm talking about this capital delta, okay, this guy becomes more and more like impulse. Therefore, as a result, the output, the pulse response, as delta goes to 0, must become closer and closer to h of t. Okay. So therefore, what we're going to do in our linked approach is we will obtain the pulse response in terms of delta, capital delta, and we will compute what happens to h delta of t as delta becomes tinier and tinier, okay, in the limit. And hopefully we will obtain the same result that we obtained in our previous lecture for the impulse response. Okay, so let's put that observation down. Since one way to describe the delta function is lim delta goes to 0, this pulse, the delta t, we should have the same relation hold between the respective outputs. That is, h of t should equal, in the limit, h delta of t. Okay. So therefore, at this point, the question is, what's h delta of t? We obtain that h delta of t, and then we attempt to obtain that limit. Okay, our expression. H delta t. Okay. So in our previous lecture, we obtained the pulse response for a pulse with general height and general width. Now we're not talking about any pulse, but we're talking about a very special pulse, okay, which in the limit gives us the impulse. In any case, we can write the impulse response as the following difference. 1 minus e to d minus t over rc t minus 1 over delta 1 minus e to d minus t minus delta over rc u t minus delta. Okay. Then it's clear that for t negative, the argument of this is negative, and the argument of this is also negative because delta is a positive number. Hence, this is 0, this is 0, everything is 0. Okay, so therefore there's nothing interesting going on for negative times, for t negative. Okay. Now, how about the future? How about for t greater than delta? Now, we don't have to worry about what happens between 0 and delta because that will become more and more insignificant as we squeeze delta further and further. Okay, so let's therefore talk about what happens for t larger than delta. Okay, now for t greater than delta, h t equals, now for t greater than delta, the argument of u of t is positive, therefore this thing is 1. The argument of t minus delta is also positive, therefore this thing is also 1. So what we have is this thing minus the thing that is multiplying u t minus delta. So let's write that down. 1 over delta 1 minus t over rc minus 1 over delta 1 minus e minus t minus delta over rc. And this thing, this exponential term, we can write as product of two exponentials. And if you do that, this is what we have. E to d delta over rc times e to the minus t over rc. Okay. Now, this one and this one, they will cancel. And what we have is e to d delta over rc minus 1 over delta, and that's multiplied by e to d minus t over rc. Okay. Now, that's the expression for the pulse response in terms of delta. Okay, and now from this expression, we will attempt to obtain h of t. And what we're going to do is, we're going to obtain h of t by simply making delta going to 0. Okay. Now, in the limit delta goes to 0, h delta of t, the pulse response becomes something, provided that that something, this thing has a limit, okay, times this function e to the minus t over rc. And that's for t greater than delta. Now, that equals limit delta goes to 0, e to d delta over rc minus 1 delta times e to the minus t over rc. Therefore, we have to figure out this limit. Okay. If you plug in delta equals 0, what you have is, this is 1, 1 minus 1 is 0, and you also have 0 in the denominator, so we have 0 over 0, which doesn't help. So what you do is you can either apply L'Hopital's rule, that is differentiate both numerator and denominator, and then retry, or we can do the following: E delta over RC equals 1 plus delta over RC plus 1/2 delta over RC square plus 1/6 delta over RC cubed. Okay. So we write the exponential function in its series expansion. Okay. And then this is e to the delta over RC. This minus 1, okay, removes this, and then you divide everything by delta. And what you obtain is E delta over RC minus 1 over delta equals, this one goes away, and then you divide everything by delta. So you have 1 over RC plus 1/2 delta over RC squared plus 1/6 delta square over RC cubed, and so on. Okay. And now in this form it's obvious what this limit should be. As delta goes to 0, these terms all vanish. Okay, delta square, and we're going to have delta cube, all the higher order terms. And what's going to be left is that constant term 1 over RC. So these vanish as delta goes to 0. Hence, the answer to that limit, the solution to that limit must be 1 over RC. Okay, so we can write that for this has to be equal to 1 over RC e to the minus t over RC. Now what we're going to do is we're going to combine the pieces. Okay, we have, okay, for t greater than delta, we obtain h delta of t, and then therefore, as delta goes to 0, we have this expression for the pulse response. So that means for t greater than 0, we have this in the limit, and for t less than 0, the pulse response is 0, therefore its limit is also 0. Hence, we can write h of t equals limit delta goes to 0 pulse response, and in the limit pulse response is such that 1 over RC e to the minus t over RC for t positive and 0 for t negative. Okay. Now this piecewise expression we can squeeze into a single expression by using our step function and write h of t equals 1 over RC e to the minus t over RC times u of t. This multiplying by u of t takes care of, it is this for t positive and 0 for t negative. Note that this is the exact same expression that we obtained in our previous lecture. Now let's also spend a few minutes on the step response for the same circuit. Okay, let's find the step response of the same circuit. Okay. And let S of t denote the step response. Okay. So h of t denoting impulse response, S of t is step response. Okay, so by definition, step response is such that you have zero conditions. Okay. Plus minus ECC R, and for the input of your circuit, we apply unit step function. Okay. U of t. Now, what we have is for T positive dVc plus 1 over RC Vc equals 1 over RC. So that's the differential equation for T positive, because this guy is 1. Okay. And then initial condition is 0. Therefore, that's a non-homogeneous first order differential equation, and we solved that equation many times, and we know the answer. The answer is VCT equals 1 minus e to the minus t over RC. Okay, for T positive. For T negative, the input is 0, initial conditions are 0, therefore everything is at rest. So therefore there's nothing to compute, and we can immediately write for T negative capacitor voltage, and everything else is 0. Okay. Again, we can combine these two pieces, and glue them by using the step function, and we can write. Okay. Therefore, S of T must equal this guy, 1 minus e to the minus t over RC, then times u of t. And this u of t takes care of the fact that the capacitor voltage is 0 for negative times. Okay. Now here we have the step response, and here we have the impulse response for the same circuit. Now, since they express the same circuit, or they're coming from the same circuit, there has to be some relation between them, okay, H of t and S of t. And that, what that relation is, we will now discover. First, let's remember the relation between the inputs, that is the step and the impulse. We have that impulse is the derivative of step. Okay. Now, here is a wild claim which says that the impulse response then equals derivative of step response. Okay. Now, instead of D, if we had alpha, okay, some constant, let's say you apply an input and you get the zero state response, and then you apply some constant times the same input, let's say alpha Vs of t, and by homogeneity you get alpha times the first response. Okay, so that's thanks to LTI-ness of our circuit. But now here's something very interesting going on. This D behaves just like a constant, even though it's not a constant. Okay, it's an operator. We're differentiating it, but still LTI-ness, okay, of the circuit allows us to treat this operator as if it's a scalar. Okay, so let's prove that claim, and the proof is quite straightforward. So d over dt st equals what? So we have, okay, this is our step response, and we can consider that as a product of two functions. Okay, here one piece and here the other piece. Therefore, by chain rule, we have, okay, the derivative of the first term, which is 1 over RC to the minus t over RC times ut, okay, plus 1 minus e to the minus trc times the derivative of the second term. Derivative of step is impulse, therefore we have delta t. Okay. Now, what this guy is not that it's a continuous function and it's being multiplied by impulse. Okay? Therefore, by shifting property, this equals 1 minus e to the minus t over rc evaluated at the point which makes the argument of impulse 0, which in this case is 0, times impulse. Okay? So if you plug in t equals 0 here, this is 1. And this is also 1 minus 1, 0, so what we have is 0 times delta t. Okay? which is 0. Therefore, the derivative of step response is this thing, and that's no other than the impulse response. Okay, so that's the end of our very short proof. Now, this raises the question: can we generalize this to more interesting situations? That is, we're talking about the zero state response. Suppose that for some input you have something at the output, zero state response, and then if you apply the derivative of that, the same input, do you obtain the derivative of the output that you recorded in the first experiment? The answer turns out to be positive. So let's talk about that a little bit. Okay, so this is true in general for LTI circuits. Okay. Let's consider the following case. This is the LTI circuit with 0 initial conditions. Here we have some input, let's call it W of t, and that input generates the output, which we're calling Y of t, and that output is, or that waveform is what we're calling the zero state response for this particular input, W of t. Then, so that's our circuit, and then by time invariance and homogeneity, we can write the following. Okay, same circuit with zero initial conditions, and this time you're applying for the input W t minus W t minus delta, and you're scaling everything by 1 over delta. And thanks to the fact that the circuit is LTI, at the output, you're going to see Y of t over delta, and then minus Y t minus delta over delta. Y t minus delta over delta. Then, if you take the limit, delta goes to 0. This, by definition of differentiation, it becomes derivative of W, and then the output should become the derivative of Y of t. Therefore, if you apply the derivative of the input, you obtain the derivative of the output, under the assumption that initial conditions are 0. So take the limit delta goes to 0. Lim delta goes to 0. WT minus delta over delta. And at the output we see YT minus Y t minus delta. And what we're doing is we're looking at the situation under this limit delta goes to 0. Since this is true for any delta positive, therefore in the limit we have to have the same circuit under zero initial conditions. This becomes in the limit d dw of t, or v dot, the derivative of w, and therefore, likewise, the output also becomes the derivative of the original output y of t. D y of t. So therefore, we discovered something quite remarkable and in a very easy way, only we use time invariance and homogeneity. And what we obtained is that this derivative operator behaves just like a scalar. Okay, so homogeneity can be extended, can be generalized to such operators. Okay, for LTI circuits. Now let's conclude let's finish the lecture by a simple example. Consider the RC circuit with input Vs of t. I have 4 ohms EC. And Vs of t, the input to the circuit, is given as the following piecewise constant waveform. 0. Pulses. -1, the magnitude is 2, this is VST volts, this is seconds. 1, 2, 3. And the question is, what's VCT? And the initial condition is 0, we ask for the capacitor voltage. Okay. Now, one way to do it is, what to do is, you go and treat the problem in a piecewise fashion, so nothing happens until t equals 1, and the initial condition is 0, therefore everything is 0 for until t equals 1. Okay. And then between 1 and 2, what you have is you have the constant input with magnitude 2, and then obtain differential equation. That would be a non-homogeneous differential equation with constant right-hand side. And initial condition is 0. Since VC0 equals 0, clearly, and the input is 0 until t equals 1, the initial condition VC1 is also 0. So you know the initial condition for t equals 1, you know the differential equation, and you easily obtain the solution. And that solution will hold for the interval from 1 to 2 seconds. And then at 2, the input changes. Okay. Now it becomes -1. So that means a different differential equation. So again, you treat that new differential equation, non-homogeneous first order with constant right-hand side. And so you got the differential equation. You also need the initial condition, which you can obtain by using the first solution that you obtain and evaluating at t equals 2. So the new differential equation, new initial condition, and you can obtain the second piece of your solution. And then, finally, at t equals 3, the input disappears, it's 0. So what you do is, you obtain the differential equation, once again, this time it will be homogeneous differential equation, compute or obtain the initial condition from the previous solution, evaluating your previous solution at t equals 3, okay, and then you get the last piece of your solution, okay, and then you can write down the answer in a piecewise fashion. It's 0 between, or time t less than 1, it's something between t1, t between 1 and 2, it's something else, t between 2 and 3, and finally it's that for t larger than 3. Okay, so it's easy, but it's a long process. Okay, there's a much shorter way, which we can use thanks to LTI. So that circuit is LTI, and it's the following solution. Step response for the circuit is 1 minus e to the minus t over RC, and RC is 2 in this case, times u of t. Okay. So for this, we know the step response. And we can write that input in terms of steps. Okay. Input Vs of t can be written as, we have 2ut minus 1. Okay, so that's that piece. And then what you do is, if you don't do anything, it will go on forever at magnitude 2. So what you want is, you want a drop of 3 units at t equals 2. So from that you subtract ut minus 2. And then finally, at t equals 3, you need a rise of magnitude 1, okay, plus u of t minus 3, okay, and that's the input in terms of step functions. Okay. Now, S of t, the step response, is the response due to u of t, and since the input can be written as scaled and delayed versions of unit step, we can use the step response to express the solution VCT for that particular input Vs of t. Okay, therefore the response Vc of t must be equal, very straightforwardly, to St minus 1 minus 3St minus 2 and plus St minus 3 equals. Okay. Now the question is, what if the initial condition was not 0? So the response, therefore, we cannot be talking about the 0 state response in that case. It's just a minor difficulty. All you have to do is, you have to remember that you can always superpose 0 input response and 0 state response. So if the initial condition was different than 0, then you compute the 0 input response for that particular initial condition. Okay, and then add to this that final piece, okay, which is the 0 input response for the particular initial condition.